Hello, welcome back. So we had started the study of cryptographic protocols. These aim to tackle and solve problems that go beyond simply secure communication between endpoints, and effectively they're kind of games that are played between different parties. So we had gone through a couple of examples and we'll still continue that route of just quickly stepping through a few examples. What we're looking at here is a simple instance of what's more generally called multi-party computation, which is a very exciting technology for many use cases nowadays. So suppose we have n parties, for example, all students in a class, and each party knows a particular number or integer, and they want to know jointly what is their sum. You can think of this as saying, consider the function f of all those numbers, which adds them all up, and what is the value of this function. So you might say, well, this is kind of an easy thing to figure out. How do you figure it out? Well, assume the parties are not co-located, and you just have, maybe you elect some leader, say party 1, and everybody sends their number to party 1. That party adds them all up and tells everyone else what the result is. The difficulty is that we want to do this also in a privacy preserving way. So there are privacy constraints on these integers, and parties don't really want other people to know what their value is. So it's a problem if party 1 finds out everyone else's values. But despite the fact that each party wants to keep their own value secret, they are actually curious to know what the sum is. So one may first ask, well, why would something like this arise? So here's a few examples. So suppose you wanted in a class to compute the average score on the midterm exam, and this wasn't made available in any other way. So the students each have a score, but they don't want to reveal their scores. They just want to know the sum, which is equivalent to the average, because the average is the sum divided by the number of students. So that would be a case of this problem. How do I compute the sum of the scores of all students without revealing individual scores? You might have some employees in a company who are curious to know whether their own salary is bigger or larger than the average in their group. But people don't like to announce what their salary is. So that's another instance of the problem. The function would allow them to get the sum, but without revealing individual salaries. A very simple example is voting. So there, each party's input is just a bit, which is a yes or no vote for some proposition on a ballot. And the sum is the tally. That's what you want to come out of the election. But of course, voter privacy means you don't want to reveal individual bits of different voters. So with those kinds of things motivating this, let's try to see if we can solve this problem. So here's the model we'll adopt, that these parties are connected through secure channels. We have now many ways to build secure channels, so this isn't really a problem. They can send each other private and authentic messages, and they will simply exchange such messages to ultimately arrive at the value of the sum of their inputs. Now, you could imagine implementing this. There would be some kind of app, you download the app from somewhere, and when you open it, it'll ask you and prompt you to enter your input, X sub I. Say your number is 55, you enter 55 into the phone. It'll also then ask you for addresses and so forth for all the other parties. And everybody who's running the protocol has a phone and has this app on it, and they all enter their numbers and they all enter everyone else's addresses. And then the app starts sending messages back and forth, and after a while your screen shows the answer of the computation, which is the sum x1 plus x2 up to xn. And you're done. Everybody now has that on their screen. But now what about the privacy aspect? The privacy aspect is that, say you're user 1, you shouldn't be able to know what x2 was from what went on in the protocol. And indeed, that will be true. If you look at the app, of course, it won't show you x2, but you might think, oh, it's somewhere in the memory. But you can look in the memory, you can take your phone apart, you can do whatever you like. It'll turn out that nowhere is x2 actually stored. In fact, your phone never discovered the value of x2, and that'll hold also for x3. So this is what we're getting at. We're getting at the math behind allowing you to create such an app. So here's how the protocol works. We'll first start by fixing a public number n such that all the private values belong to z mod n. So they're all between 0 and n minus 1. Now, that may sound like an assumption about the maximum, which is true, but usually it's quite easy to know what this number is. For example, if you're voting, all the exabytes are bits, so we can set big N to 2. If it scores on an exam, they're all between 0 and 100, so we can set big N to 101, and so forth. Now let's let M be the number of players multiplied by this maximum value. Okay, now just mathematically let S denote the sum we're trying to compute. Of course, we don't ahead of time know what it is, but it's just as far as notation goes. What the protocol will do is it will use modular arithmetic, and as a result of that, it will compute S mod M. So, of course, the goal is just to get S, not S mod M, but then you notice those two are identical. S mod M equals S. Why is that? Because M is so big that S itself is smaller than M. So S mod M will be S. Fine, so we're now trying to compute S mod M. So what do these parties do? So each of them takes the same step. So let's consider one party, say party I. It's going to create a kind of representation of its own secret input. Remember, it has a secret input x sub I. What it does is it picks a whole bunch of other numbers, n of them, all in Zn, and in such a way that they add up to xi, to its own value. Of course, this addition is modulo m, which is why we want mods over here, not as integers. Now, besides the fact that they add up to this, they're random. You can imagine picking all of them at random except one, which is set to solve the equation. And now what it does is that it sends each of these values to a different player. So it sends xij to party j over the secure channel that xi has with party j that we assume. So you can think of the process now as represented by this matrix. Player 1 has x1. It writes x1 as the sum of these four things. Here there are four players. It sends this to player 1, which is to itself. It sends this to player 2, this to player 3, this to player 4. Okay, so let's now look at the end of this round, which is executed by all parties, let's say in parallel, as to what is the position of a particular player. Let's look at player 1. What does player 1 now have? Well, of course, it has its own input, and it received this from itself, but it received this from player 2, this from player 3, this from player 4. So column 1 represents what player 1 knows at the end of this round of the protocol. But now you observe that what it knows here is not revealing information about other values. If player 1 wants to know something about x2, this value leaves it clueless because this value is completely uncorrelated to x2. It's only going to give you x2 if you add in all these other values, and player 1 has no clue what these other values are. And individually, that's true for each other player as well. So far we've preserved privacy while somehow making the input of each individual player a kind of collective presence that they all have. And now, however, we want to get the sum of those inputs out without actually reconstructing them. The observation for that is that look at the sum of all entries in the matrix. The claim is that's the sum we want. It's the sum of all inputs. Why is that? Because this row adds up to x1, this row adds up to x2. etc. So if you add up all the rows, you're adding up all of these, which is S. But adding up all the rows and getting the sum of the entries in the matrix can also be done by adding up all the columns. It's the same sum. So player 1 having all these values can form this one sum, player 2 having all these values can form this one, and so forth. So each player computes the sum of all the values it received in the prior round. And then they simply broadcast those values. So they send their column sums to every other player. And now everybody has these column sums. And of course, if you add those up, you just get the sum of the entries in the matrix, which is what we're looking for. And so everybody now has that sum. So that's the protocol. Now you still have to wonder, is there some privacy violation in sending out these sums? But you can do an analysis of this, and it turns out that you can see that it isn't. So for example, consider party 1 at the end of the protocol. What does it know? It knows its own input, it knows these values, and it knows the sum, all 4 sums. But this actually doesn't tell it anything about, for example, what x4 is, because there just isn't enough information to figure that out. Furthermore, you could imagine that 2 people in this protocol come together and try to pool their information to figure out a third person's information. And even that will fail up to some extent. So if parties 1 and 2 get together, they will still not learn what x4 is. If parties 1, 2, and 3 get together, they will learn what x4 is, however, naturally. So it's fun to play with this. If you want a project, you can try to do something like that. What we had just seen was actually a very special case of a much more general problem, a very intriguing and powerful method called secure computation. And the general statement of the problem is that you continue to have parties 1 through n, and you continue to have each of them has a private input. These are no longer necessarily integers in some range. They could be strings of any type. And they want to compute some function on all their inputs, but in such a way that information about their individual inputs is not revealed by that process. The change is that this function f need no longer be the sum of the inputs. In fact, it can be completely arbitrary. So any function, and the claim is that any function can be computed privately in this way. Technically, it's what's called n/2 private. That means that it remains private even if up to half the players collude to figure out inputs of other players. But if more than half collude, it may break down. Now, one may ask, well, how on earth does one do that? It's not at all as simple as the sum. And what the solution is that you actually start with a program for f. You write code, Python code or C code or whatever, and then you think of that as a circuit, so as a bunch of gates. And then you have a kind of encrypted gate-by-gate computation of the circuit. So there's a way to have circuits running on encrypted inputs and giving you encrypted outputs. And eventually you decrypt the final output, and that gives you the result. So this is, of course, hiding a whole bunch of very complicated stuff, but that's very, very high level what happens. So a good takeaway is that something like this is actually possible. Now, nowadays, it's a very hot topic. People are building lots of these protocols. Some of the usages that you can think about are privacy-preserving machine learning. So what often happens is you have 2 entities, like 2 hospitals, each has a database or data set of patient information, which they regard as private. But they nonetheless want to pool that information to get some kind of model. And so what you would do is you would kind of run a secure computation protocol which creates this model. And there are many other such things. Here's one interesting one. It's called the Callisto project. And as they say here, the problem is sexual assault and the process of reporting it by victims. So victims don't feel confident about reporting it. And so what they've done is they've built a multi-party computation-based tool called Callisto, whereby you can somehow do a kind of private reporting, and the system checks for matches of your report with other complaints and things like that. It's a very interesting sort of effort. Another fascinating protocol is zero-knowledge proofs. So it's a way to convince someone your claim is true without revealing how. And we'll look at that in a little more detail in the next segment, so I won't talk about it further here.